of production of uh, um, batteries, there's a exponential demand for these metals and materials that comprise the lithium-ion battery. So as we see over the next several years, this demand is going to increase exponentially, and it's definitely, and by 2030, we'll realize that it's in excess of $100 billion industry. Okay, so we have a list here of the types of metals, okay, that are used in a metals and semi-metals that are used in a lithium-ion battery. But what are their main functions and what do they do? So, so what makes up a lithium-ion battery? So at the anode is copper, which makes up about 17% of the battery by mass. Okay, this copper electrode is coated with graphite, which comprises 22% of the battery. And then the cathode material, which has been a lot of the focus of the recycling industry because it's, you know, the most valuable component. This is where you have your lithiated metal oxides, okay? And that is then attached to a aluminum current collector, which current is facilitated by using carbon black and a fluorinated binder, okay? Now to keep the battery from shorting out, right, we have a separator, and then also the electrolyte, which comprises about 15% of the battery, also contains lithium salts to facilitate the transfer of lithium from anode to cathode for charging and discharging cycles. Okay, so you can see, so the main metals here, right? Copper, aluminum, lithium cobalt oxide, these are lithium nickel, manganese. And we see that over the years, the NMC nickel cobalt manganese chemistry has evolved, but initially a lot of the work was in the lithium cobalt sector, which I'll talk about a little bit later as to why. But we see one of the challenges here, right, is that these battery chemistries are changing with time, right? So if we are to recycle these batteries, that a competitive process should be able to recover a wide range of variability to meet the global demand. So looking from a mining and metallurgy perspective, this can be viewed very similar to natural ore bodies, right? But the advantage we have here, right, is this is more defined, right? So we could look at this as, you know, urban mining as some low-hanging fruit, if you will. Okay, so one of the things about these materials is that the majority of them are not produced domestically. Less than 1% of these critical materials for batteries are produced in the United States. So some recent estimates and approximations, the majority of lithium is produced in Australia and South America, Chile, Argentina. Down where they have the Australia is mainly hard rock mining, right? Where South America is mining from brine resources. Okay, the United States produces less than 1%. We only have currently one operating facility, which is in here, the state of Nevada. Similar things are observed with nickel, where the vast majority of this material is mined and manufactured and produced over in Indonesia and the rest of the world. Flake graphite, which is actually from natural graphite, which is actually needed for the anode materials, the vast majority is produced over in China. And then cobalt, where we see the vast majority comes from the Republic of Congo. So with all of these key materials being produced overseas, the U.S. is highly dependent upon foreign production. And as we have observed over the last few years, and currently this can not producing a lot of materials domestically can have interruptions to supply chain, right? But more so from a a sustainability and environmental standpoint, doesn't really make much sense to move all of this material all around the world, right? So it is of our advantage, not only as a nation, but also from an environmental perspective to produce, manufacture, and recycle these materials as much as we can domestically. So with this, we see this at ABTC, we see this as not challenges, but opportunities, okay? And what we have developed is kind of a three-tier approach to addressing these challenges. From the base, from primary metal exploration and extraction, to developing this resource, to also then recycling these materials. Now, I forgot to mention my background a little bit. I grew up in northern Michigan. My family, we had an excavating business. My first job was working on a rock crusher. I think the only reason why Dad put me on there was because I could fit between the screens and change them without having to take the whole damn thing apart. Okay. And also we had a metal scrap recycling on the side. So I've been in the dirt and scrap metals kind of my whole life. But one thing about recycling metals, unlike any other materials, right? You can recycle metals an infinite amount of times. Whereas, say, plastics and fibrous materials, okay, they can lose their integrity, right? But metals in their metallic form are chemically indistinguishable from one another. So you can recycle it an infinite amount of times. So looking at from a circularity perspective, metals warrant this type of operation. Now, it may seem like some violation of the second law of thermodynamics, right? There is no such thing as a free lunch. So, but to make this happen does require work, energy, okay? Not saying that, okay? But, so with this circularity, we have developed processes that can take not only end-of-life materials, such as batteries, but also waste that is generated from these industries, and we can accommodate those streams in our recycling process. Now, we also must understand that to make the circularity work, we have to have a critical mass of materials. Now, this can only be supported by the production of primary resource materials, such as lithium mining, cobalt mining, nickel mining, and so on. So there still is a need for the production of primary resources of these metals, but we can develop this circular economy by utilizing this approach. One thing I should also mention is, anybody know what the most recycled material in the world is? Most recycled, you think aluminum, it's actually lead acid batteries. They're the most recycled material. Nearly 100% of lead acid batteries are recycled. Now, this was through industry and policy, that all lead acid battery manufacturers had to basically make the same type of battery. And also, when you go, if your car battery goes dead and you go to the auto parts store, they have a core deposit, right? You can't just get a new lead acid battery. They require to give you an old one, a deposit. So there's a financial incentive to return your lead acid batteries. Now, without saying too much about lead, it's in our environmental and health interests to recycle these batteries, because lead can have some severe toxicological effects, right? Although it makes nice white paint and so on, so that's an example of an industry that was able to really close the loop. So we can almost make a similar approach with lithium-ion batteries. So with this, we're taking a dual track approach to primary resources. So in addition to our recycling technology, we're also developing sustainable and environmentally sound extraction technology. So this is to help strengthen the domestic supply and decrease the U.S. dependence. So as we saw, there's several metals. I really like talking about metals a lot as a metallurgist, but I've decided to limit our discussion today to lithium, much lighter topic here. Now, I think lithium is a very fascinating metal because the only other two smaller elements are hydrogen and helium, which are gases. And then the next one is a metal, lithium. So it is actually the least dense element of all of them at room temperature, similar to, so specific gravity is about 0.5. There's two naturally occurring isotopes, lithium-6 and lithium-7. There's an interesting thing about, anybody know why 7-Up is called 7-Up? Lithium-7. It's an isotope of lithium. And back in the day, they used to put lithium citrate in 7-Up. As I'll show on our next slide here, that lithium is actually considered the penicillin of mental health and used to help patients with bipolar, schizophrenia, and manic episodes. So it really kind of calms you down. So this is, so maybe it was then to just kind of calm people down for a little bit. Right. But the reason why it's used in lithium-ion batteries is because it has a very high standard electrochemical potential. So you can get this large voltage difference with these batteries. Now, lithium is actually, in terms of crustal abundance, quite abundant, actually. Very similar to chlorine, sulfur, and phosphorus in terms of crustal abundance. So we do have quite a bit of this lithium distributed on the planet. Okay. Now, just some light reading here. One indication of maybe one metric to look at of an emerging field is looking at the scientific literature and the published literature. So some data I collected the last few years of keywords such as lithium resources, recycling, absorption, mining, purification, and so on, of technical literature that contains these words in the abstract and title. We see an exponential increase over the last 20 plus years of now some 18,000 publications or more over the next few years in this area. So this has become a very hot topic in terms of research. Okay. Now, where did all of this come from? Well, all metals we have, right, came from the Big Bang, right? But lithium has demonstrated to be a very, lithium is a very mobile species. It likes to move around quite a bit, especially in geological and aqueous systems, right? But it's not only moving around quite a bit there, but also in the cosmos. So this lithium cosmological accounting has been a challenge for a number of years. It's not until recently that a lot of cosmologists and astrophysicists have been able to figure out where actually all of our lithium is coming from. Because as they look at things and do the accounting, we have a lot more lithium in our universe than what we really should have from the Big Bang. Come to find out that actually most of the lithium that we see comes from cosmic ray collisions and mainly from exploding stars. So as I like to, I think it's fascinating to think about that the batteries that you use and the electronics that you have and the lithium that's in there was either the first blink of a universe or the last blink of a star. Okay. So what are some of the first uses of lithium? In prehistory, actually, lithium has been found in ceramics because it works as a great glaze, gives a nice glaze and hardened shell in thermal resistance for thermal shock to these ceramics. So historically, it's always been used. It's been the largest use actually for lithium. Currently, primary resources, meaning resources that currently contribute to the economy, is spodumene ore and continental brines. Whereas secondary resources are those that are still in development but have yet to come online. So these resources include claystone, which we're very familiar here in the state of Nevada, geothermal brines, oil field brines, low-grade continental brines. Geothermal brine example would be the Salton Sea. Low-grade brines would be, an example would be the Great Salt Lake. Lithium-ion batteries and waste from the industry. And also there are some carbon minerals that contain actually some several hundred ppm to 1,000 ppm levels of lithium. And as I mentioned, lithium has been known as the penicillin of mental health. So actually, just a kind of timeline, I'll kind of go through this a little bit quickly here, kind of some facts and figures about lithium. About 40% of global resources are found in hard rock minerals. Not hard rock, but hard rock and clay minerals, while 60% is found in brines. So some recent estimations, kind of back the envelope calculations from several resources, that global resources are about 65 to 70, almost even 80 million tons of lithium. That's a metal, that's metal basis. I like to mainly report on metal basis, where a lot of maybe other literature you'll find is lithium carbonate equivalent. So that's based on the mineral form. By USGS report, there's currently 21 million tons of reserves. These are resources that can be currently extracted now, with potential up to 86 million tons. Now, the largest mineral resource is the world's ocean. So it's about 0.18, it's about 180 parts per billion. So that gives us about 200,000 million metric tons in the ocean. It's a lot, but it's very dilute. Okay. Some of the first reports of lithium minerals is in the 1790s, and it really wasn't isolated and reported as an element until the early 1800s. And first separated its metallic form commercially in the 1920s. Now, historically, lithium has been, its main market application has been in ceramics, but it's not until really the advent of the lithium-ion, rechargeable lithium-ion battery, which was developed by Yoshino in '91, that lithium really kind of took off. Now, lithium-ion batteries aren't something new. They're actually research in this area dates back to the 1960s. But some of the earliest modern day lithium, the earliest modern day lithium-ion battery that looks similar to what we use now was actually developed in 1976. Okay, and then in the 80s, there was they switched the cathode material to the lithium cobalt oxide. So this was some of the first uses for it. And then in the 80s, there was some work done on intercalation of lithium with graphite. And in 1991, this is when the rechargeable battery, and recently Whittingham, Goodenough, and Yoshino shared the Nobel Prize in Chemistry for the invention of lithium-ion batteries. To just a few, in recent days, that now estimates of 2020 global production of lithium-ion batteries is in excess of 760 gigawatt hours. So domestic, so kind of shifting gears here on domestic lithium deposits. 21 global lithium production was approximately 100,000 metric tons, and the USGS has identified over 9 million tons of lithium reserves in the US alone. Now, there are a few areas that actually have appreciable amounts of lithium that can actually contribute to the supply chain. Piedmont spodumene, this is the spodumene tin belt in the Carolinas. Okay, actually historically this was one of the largest lithium producers, but it produced for some time and then the mine shut down, and now they're looking to fire back up. Smack over down in Arkansas, these are lithium rich brines, and then there's also the Salton Sea geothermal brines, and then, as I mentioned, the Great Salt Lake, and then there are several projects in the state of Nevada related to Nevada sedimentary claystone. Now, they all have their positives and negatives, right? But currently, right now, the only one in production domestically is a brine operation in Nevada. So just kind of, I had to put some, since I didn't include any differential equations, I know you're all graduate students, right? So I figured I should put some clay structures up here to at least hit that mark. So one interesting thing about these sedimentary clays, okay, they're very fascinating materials actually. And these clays found in Nevada are basically these phyllosilicate minerals of alternating layers of tetrahedral and octahedral sheets. Now, depending upon the order of these, okay, 2-1-1 or 1-1 layer or 2-1 layer or combinations and permutations thereof will dictate the overall charge on this mineral. Now, joining of these sheets results in a negative charge balance and substitution of various elements in various sites, and then balancing it with other cations attribute to this overall large charge, negative charge on these clay particles. Now, this charge variability is a very important feature because it induces occupancy of layer spacing for exchangeable sites of cations. Right. So this is an important feature of these clay materials, right? That we can utilize for extraction. Now, these negative layers are then compensated by these positive cations, which can be sodium, potassium, calcium, or lithium. Right. So they can either be in ion exchangeable sites or within the actual structure of the material. Now, these clays are, I would say, it's a soup. You can have yellitic, smectitic, hectoritic kinds of clays in these materials, all in the same site, really. So these mixture of clays, it also, not only are the clay minerals there, but you also have quartz, calcite, feldspar, dolomite, and pyrite. And this is consistent with what's found throughout the, especially in the Tonopah area, and even from the northern part of Nevada through the Tonopah area all the way down to why am I spacing on where's Cypress used to be? Clayton Valley. Now there's all of these areas, these clays have experienced different geological processes. So there's going to be slight variations from deposit to deposit. So I'm just speaking on a very, very general term in terms of these clay materials. Okay, so with these, we can have kind of three different types, really: layer and interlayer cations, right? Layer and hydrated interlayer cations, and then layered and octahedrally coordinated cations in the inner layer, right? So we can have kind of these three different types of clay minerals that we have to work with. Okay, so presents some excellent challenges in terms of extraction. So talking now, switching gears, talking about the projects that we have, is we have over 10,000 acres of claims down just outside the town of Tonopah, Nevada, which is about halfway between Reno and Las Vegas. In 2022, we completed our initial drill hole exploratory campaign. And one nice thing about the Tonopah area is actually it's a very mining friendly area, historically gold and silver. And it also is very close. There are major power lines that actually run east to west, north to south. So it's strategic. It has a nice location in terms of not only just the town, but also location to utilities. Summarizing our initial drill campaign, we have several drill holes that have samples in excess of 1,000 ppm lithium with shallow overburden and consistent lithium concentration with depth. Okay, so looking, here's an example. So we have, this is a link here. Actually, I'll go to this, see if this works. I wonder if they can see online, probably not.
Sharing.
It's not sharing. Okay, so I would suggest just going to the link. This is actually a 3D rendering of our lithium deposit, outlining where our drill holes are. And we can see that 100% of our initial drill holes have lithium in excess of 300 ppm, with almost 90% greater than 600 ppm. And then looking at our deposit, we see that almost over the entire claim, we have lithium in excess of 300 ppm. And as we move to higher and higher grades, these plots show where the actual optimal pits would be to start our mining process. So we see that all of it, the whole area is basically greater than 300 ppm. A good majority is greater than 500 ppm. And then we have the concentrated regions you can see here on the far right figure. Now, looking at all of this, recently we had a third party conduct our inferred resource report, which is SK 1300. This is done by Respect, which is a company located here in Reno. And going through all of the data that we have collected through our drilling campaign and pit optimization, we have reported that this classifies the resource as inferred and indicates that it potentially contains almost 16 million tons of economically accessible lithium carbonate equivalent. What does that come down to? That means that we have a cutoff grade at 300 ppm. And in terms of lithium metal, that's 2.9 million tons of metal in this deposit. This is one of the largest known lithium deposits identified in the United States. And our inferred resource report is also available on our webpage. Okay. So to move this so we have a very good resource that we've shown. We've actually received quite a bit of government support to actually develop a lot of these processes. So back in 2001, we received a $4.5 million grant from the U.S. Department of Energy to field demonstrate the leaching, purification, and conversion of domestic claystone resources to a viable sellable product. We've demonstrated on the bench scale, validating that we can manufacture lithium hydroxide at battery grade using this first of a kind selective leaching technology. It minimizes the amount of chemical reagent that we use. We have gone through our first period of this project. We are now starting our second period of the project, which is the construction and operation of a multi-ton per day field demonstration unit to demonstrate this process. This work is also in collaboration with DuPont and University of Nevada, Reno. Subsequently, in this fall, we also applied for a much larger grant and for a $115 million project. And this is to actually construct a large-scale demonstration, plant to demonstrate not only the extraction, but refining of this claystone product into lithium hydroxide. Using a first-of-kind process, we'll initially start out at about 5,000 metric tons per year of product and scale up to 30,000 metric tons and more. This is also, this facility will provide over 150 new jobs, and also the grant heavily focuses on workforce development. This was part of the infrastructure bill, and as a result of winning this grant, our company CEO, CTO Ryan, was actually interviewed by President Biden for the actual kickoff of this event. So this project will actually be starting here sometime this year. So with all of this, I wanted to throw this in as well, but with all of this, there's a big boom in this area. So workforce development for mining and metallurgical engineers is greatly needed. A recent study by McKinsey and Company of mining leadership reports that talented shortages are holding back production targets and strategic objectives. Three kind of large areas where they're finding difficulty in recruiting young talent is in mine planning, process engineering, and data science and automation. And we see that responses of young people, if they would consider working in this area or not, and also the trends of mining engineering students in the United States and Australia has been on decline, but this is in 2018. Maybe this trend is hopefully on an upward trend from here. But this is, I'd just like to make this point that your students, your positions in the future, you'll have very many opportunities related to mining and engineering, metallurgical engineering, as the need to support these industries is very high. So I'd like to switch over now to kind of wrapping up a little discussion about our recycling process. There are essentially two ways to kind of recycle, two general approaches to recycle lithium-ion batteries. One is through a pyrometallurgical approach, and the other is through a hydrometallurgical approach. Now, through a pyrometallurgical approach, you'll have usually lower recovery, but you're also going to lose a lot of valuable materials. One is mainly the actually graphite material, because that one's actually being burned. Whereas if you take maybe a hydrometallurgical approach, you can recover nearly all components of a lithium-ion battery that can potentially then be recycled. However, the conventional approach is expensive and uses large amounts of reagents. So what we have developed is an advanced hydro process that has very high recovery rates and actually has a low chemical footprint. And some of the keys here are the demanufacturing process of the batteries. Many of the founders of our company and many of the engineers in our company actually built the gigafactory and the manufacturing lines of batteries. So by developing these lines and learning how these batteries actually fail, these failure modes, and then exploiting these in reverse, you can actually then take apart a battery and remove targeted elements that actually can improve your overall process efficiency. So the strategy to this is very much circular. That by utilizing a demanufacturing process and sorting and then recycling a lot of the materials and chemical reagents in this process, we can then not only take module cells and manufacturing waste, we can then run this through our process and produce our nickel, cobalt, manganese sulfate, and lithium hydroxide products. So with this approach, circular approach of regenerating and utilizing not only our water and chemical reagents, we have a much lower operating cost and not a very capital intensive operation as well. No high temperature operations are utilized, and we have as I mentioned, much lower chemical consumption rate. Sorry about this slide, just kind of covering how this all kind of started was our founder, Ryan, was involved in the 2019 BASF Circularity Challenge. BASF is one of the largest chemical companies in the world. And out of 100 applicants, ABTC was selected as the sole winner of the Circularity Challenge. From here, we were then also awarded a $2 million grant from the United States Advanced Battery Consortium. And in this project, we're working with not only BASF, C4V, but also the US Battery Consortium, which is Stellantis, GM, and Ford. And in this project, we actually take waste material, produce battery grade transition metal sulfates and lithium hydroxide. And then which we've already demonstrated we can do. And then the next is we actually then take these materials and then are going to make actual synthesized active cathode materials, which will then be put in batteries to test. So so fabricate large format automotive cells utilizing the recycled materials and checking the performance to show. So this will be an actual demonstration of taking recycled materials, producing battery grade materials, putting back into an electric vehicle and demonstrating the performance. Okay. So to meet these battery grade specs, we've actually worked with our partner BASF on what are those actual specs. So we have developed a certificate of analysis that we can then actually produce to make these materials to their specific needs. Sorry, I'm kind of running out of time here a little bit. And just recently in the spring, we applied for a DOE grant and to look at new advanced separation methods for our recycling process, working on actually anode materials, cathode materials, and new ways to actually do crystallization of our products. So this project was, we submitted this in spring 22, and this project involves, I think 9 or 10 actually universities. There's three national labs, half a dozen other universities actually involved in this project as well. So this will be bench scale and skid and pilot scale demonstration of these new integrated technologies. So how do we do all this? We do it with a lot of good, talented people. And our research and development team, I just wanted to highlight, actually, there's a good chunk of us that are UNR alumni from not only mining and metallurgy, but chemistry, chemical engineering, and environmental science as well. And as I mentioned, we also have one of your undergrads working as an intern as well. So with that, summarizing that this is a fast-paced moving area that is going to require that will be growing rapidly. A lot of our technology has been we've received a lot of support from government agencies, and also we've developed very tight partnerships with industry leaders such as BASF, DuPont, and U.S. automakers. So with that, I will say thank you for the time, and I have opened it up for any questions you may have.
Question. So I want to know, like, how much water is required to process lithium batteries from mining till getting the battery?
So the question was how much water is used. That is going to depend on the type of approach that you use. A kind of classic leaching approach is going to use substantial amounts of water. I think you'll, but a lot of this water actually can then be recycled. Okay, so there is a bit of water that's needed for it. Quantification, I think, of that value depends on the chemistry that you're doing, and also the type of ore body that you have. So, it's a very variable question. So it's all going to depend on the size of the plant, the mine, the deposit, the chemistry that you have.
You had mentioned at the beginning that you have to reach a certain critical mass in order to make the whole process work. I just wanted to know how far along you are in that. You're producing EVs right now and out there running. I'm assuming you guys are kind of waiting for some of those to restart life and then start doing this process, or to scale it to a big one.
Sure.
So how far
So we're actually starting phase 1 of our recycling process, which actually will be up and running sometime this year. And one comment I'd like to make about the critical mass is yes, batteries have about 10-year lifetime or so, so there's a lag period until that volume of battery actually makes it around. But the manufacturing of these batteries actually produces some waste. So to actually supplement that, we can take industry waste and use that waste or off-spec material that doesn't need it, process that, and use that as feedstock to then make battery-grade materials. So, so you don't have to be as dependent on just battery feedstock in the process industry waste to get us to that over the line to that next point.
When you're at full production on both, what is the relative primary production rate versus recycle rate? Which one's going to give us more?
Which one's going to give us more lithium? So I would say the mining, the primary production, because we're looking at 30,000 tons per year of final product to even we're looking to scale up to over 100,000 tons of product per year. Whereas the battery recycling, we're looking to start out at 20,000 tons of battery feed. Right. So right. So initially, so that's why mining and extraction of lithium is vitally important to sustain this type of ecosystem. So they're trying, recycling is quick to get processes up and running, but the production is low, whereas mining takes a longer time, but will actually support a whole industry. Yes.
Talk about three pathways which you are addressing. I don't know if there's anywhere those three pathways connect or are they very independent? Talked about the battery ion recycling, you talked about metal extraction.
You're talking about hydro,
Oh,
and the
This one.
Are they very independent? There's a point where they need.
So with the, they're actually kind of all interrelated. Although these two are more connected than I would say with the recycling, right? But eventually the materials from the primary resource will then eventually make it back into this recycling loop, right? So, but to kind of quickly answer your question, I would say they're actually all related together because some of the processes are actually from one to the other are similar. Some different parts of the whole system are different, but there's some key aspects of both operations that are very much similar.
For example, at what point is the lithium from the primary resource needed for the recycling?
So, sorry?
You said they are interconnected. Like, for example, at what point in the battery recycling is there need for lithium from the primary resource?
I think it's kind of the other way around. Yeah. That answers your question. Oh, maybe we can talk. Maybe we can talk later. Yeah.
Sure.
You said about the uniformity or the kind of standard manufacturing of let's say battery that helps all the batteries easy to recycle. Is there an initiative in the lithium batteries similar to the type of motion to make all of them more recyclable?
More recycled. That's a very good question. And that I think has to do with the end use OEMs and actually policy that's in place. Currently, I don't believe there is any policy or regulation in place to do that. Would it make this easier? Yes. Because then also you would have a better idea of what kind of materials you have coming into your process, right? Not as much variability. That's more of a higher level, I guess, a business decision and so on. But I think that would require quite a bit of policy and regulation. is it going in that direction? I don't know. I can't really comment on that. I work on taking them apart and doing the chemistry. So there are definitely other folks that are involved in this policy that could probably answer that better than I could. I could take one more and then I do have to go because I have a call I have to hop on.
Thank you so much. Have you ever done any experiment on sample or sample to separate lithium so far? And another thing, your grade is 560 ppm. And this is lower than Tucker Pass. Tucker Pass is more than 3000. Does it make a problem in the process?
Okay, so I can quickly answer your question. Your first question, yes. We've done an extensive, actually, work on our oil. The second question, the thing about concentration, right? One way around this too is actually just then running more material through the process. Yeah. Does that answer your question?
Yeah, thank you.
I guess just one quick,
When you got one quick one.
1/2 a second.
Yeah.
How much of the lithium is in the electrolyte compared to the electrodes?
Hmm.
And is that a big problem? Because I'm sure everybody has a different recipe.
Actually, it's pretty much pretty
Is it
similar.
nitrile mostly mainly, or-
It's dimethyl carbonate and lithium hexafluorophosphate.
Okay, so it isn't an
Right.
organic.
It is it's organic, but then you have this lithium salt, right? And all of them pretty much use the LiPF6. Now, there is an advantage of actually collecting that electrolyte and recovering it. The challenge is most of the time in dead batteries is probably oxidized. So regenerating the electrolyte, although the volume isn't there, I think there eventually could be some economics to it. Sure. And sorry, I do have another meeting at 1 o'clock. I gotta take a hard stop here, so.
Thank you so much. Next meeting will be, next webinar actually, will be on April 21st. Michelle Ash